Avogadro's number is an important grouping number in chemistry. And in this video, I'll talk about what it means and how to use it. First, why would you need this idea? So let's say that you need to count a lot of beans fast. Measuring is quicker than counting. So let's imagine that you're an elementary school teacher and you have an art math idea for next week that involves dried beans. It's Friday morning and all of your parent volunteers have just called in and said they can't come today to help. But for next week, you need 100 beans of 6 types for each of your 30 students. And you don't want to spend the weekend counting out 18,000 beans. What do? Well, you took chemistry and you understand how mass works. You have a decigram balance. And so, for example, here I have lima beans, 10 piles of 10 beans each. I collect my lima beans, 100 lima beans. Tear my balance with a weigh boat on it. Add 100 lima beans. And I now know the mass of 100 lima beans. It's 120.5 grams. So I can pour those in a bag, and then for the next 100, just pour from the bag until I get 120 grams. Weighing is much faster than counting. So in this scenario, the would-be elementary school instructor can measure out the mass of a group that we called a beetle. What kind of groups are there? Well, there's a lot of grouping numbers, but let's look at these. How many in a pair? 2. How many in a dozen? 12. How many in a beendle, which is abbreviated without the E? It's a counting number, and we can count to 100, so it's a group of 100 items. Does it always have to be beans? No, it doesn't always have to be beans. Just like dozen doesn't always mean eggs. I would like 3.5 dozen eggs. How many is that? 3.5 dozen times 12 eggs per dozen is 42 eggs. But does dozen always mean eggs or cookies? Maybe I would like a dozen potted ferns, please. How many plants is that? 3.5 dozen at 12 plants per dozen is 42. Dozen means 12. And in the same way, mole means 6.022 times 10 to the 23. That large group of what? Anything. You can have a mole of anything. What sort of things are we going to count? What sort of smallest units? We're going to begin with atoms. And then we can talk about molecules, groups of atoms sharing electrons in a covalent manner. Or we could talk about the ionic version of that called a formula unit. The unit that makes up the lowest whole number ratio of cations to anions. Or we could talk about the ions themselves. So what are we going to use moles for? Counting atoms, molecules, formula units, and ions. But back to our bean example. So I would like 3.5 beendle lima beans. How many beans is that? We can do that same math. 3.5 beendle at 100 beans per beendle is 350 beans. And for sig figs, which you know are important, here I'm starting with 2 sig figs. And this number is exact. So this number is good to 2 sig figs. If the bean vendor didn't want to count them out, though, what mass should be weighed out? Well, because the person is asking for lima beans, and we know that a beandle of lima beans is 120.5 grams, we can use that equality, which is not defined, it's measured, so it has limited sig figs, to come up with these ratios. 120.5 grams of lima beans per beandle, or a beandle is of lima beans has a mass of 120.5 grams. Which way we decide to use this depends on which way we need to use it to solve the problem. So if the vendor didn't want to count them out, what mass, we're headed to grams, should be weighed out? And because we're headed to grams, this is the version I'm going to use. So we begin with the given, number plus units, 3.5 beandle of lima beans. And then we're going to use this ratio. Lima beans are pretty massive. There's 120.5 grams of lima bean in the group we call 100 beandle of lima beans. So I started with 2 sig figs, and we multiplied by a measured value, 4 sig figs. My answer has 2 sig figs. So starting in this chapter, we're going to be very particular about units. I can't just say grams. I need to say grams of what, and it's grams of lima beans. If the buyer wanted garbanzo beans, would it be the same mass? Well, no. Garbanzo beans have a different, they're smaller. There's less mass per beandle. A beandle of garbanzos has only 50.4 grams of garbanzo. So I'm putting down the unit, which is a group, beandle, and then I'm being specific about what kind of bean, garbanzo. And then I'm going to use this relationship in a way that the units cancel properly. So I'm going to need beandle on the bottom. And beandle is 100 of anything, but I'm talking about garbanzos. And then the particular mass for a beandle of garbanzos is 50.4 grams. We started with 2 sig figs. This relationship has 3 sig figs because it was measured. And we're multiplying and dividing, so we go with the smaller number. Because this number is closer to 180 than it is to 170, I would say 180 grams, but that's ambiguous because I have a whole number ending in 0. So let me say 1.8 times 10 to the 2 grams specific of garbanzo beans. Does it make sense that 3.5 beandle of lima beans would be a larger mass than 3.5 beandle of garbanzos? And the answer is yes, because lima beans are just bigger beans. Okay, so we're going to practice that. If we want to go from beandles to beans, this works for any kind of bean, and the relationship is 100 beans in the group that we call beandle. But if we want to go from beandle to mass, we have to use a beandiotic table because we need to be specific to the particular kind of bean. And then if we wanted to go from mass to beans, we would have to go through beandles. So these problems that I'm working are a metaphor for things on the periodic table. Here we go. How many beandles are 662 lima beans? So play along with me. 662, and I can either say lima bean beans, or I could say beans, that's the unit, that are lima beans. I'm being specific about what kind. Well, 100 beans is a beandle. And I'm talking about lima beans, so I'm adding that. Beans that are lima beans cancel, and I'm left with a beandle of lima beans, which is a grouping number, just like mole is a grouping number. And so I get 6.62 beandle of lima beans. How many garbanzo beans are in this many beandles? Is that specific to garbanzos, or is that just units in general? And the answer is it's just units in general. 0.59 beandle of any kind of beans, because it's a grouping number, is 100 beans per beandle. I happen to be talking about garbanzos, so I'm going to add that in there. So 0.59 beandles is 59 garbanzo beans. To go from the individual units, like atoms, ions, molecules, and formula units, to the grouping number, I'm going to use the number that is the number of a beandle, the beandiotic number. And whether I multiply or divide just depends on which direction I'm headed. Now, if I'm asked about a specific kind of bean, and we're talking about a mass, I need that beandiotic table. So how many grams are 155 white beans? I'm starting with the given, 155. White beans are actually navy beans, which is a little bit confusing. And I'm talking about the unit, the individual bean. And if I want to go from grams, which is a mass, to beans, I have to go through beandles. Well, 100 beans of any type is a beandle. And I'm talking about navy beans, which are also called white beans. I don't know. In the Navy, do they eat a lot of white beans? Very confusing. And then a beandle, the mass that goes with that group for white beans, I have to look up on the table. And it was 16.7 grams of white beans, or navy beans. Okay, so 155 divide by 100 times 16.7 is 25.885 grams. We started with 3 sig figs. This is unlimited. This is limited to 3 because it's a measured thing. My answer is good to 3 sig figs. This number is closer to 25.9 than it is 25.8. We're talking about mass, and then I have to be specific. I can either call them navy beans or white beans because they have 2 names. I don't know why. Okay, now, these 2 tools, the idea of we can use the meaning of the unit and we can use a table that tells about specific kinds of smallest units, beans. We can add those to our bag of tricks, and now we can answer questions using conversion problems like we've done before. And that's what we have in number 4. Here's a 1 pound bag of lentils. So I'm starting with 1.0 pound of a lentil. And I'm headed to how many individual beans. And so first I want to make a roadmap. I'm going to go from a mass in pounds, and I'm headed to individual unit beans. And I've said before, to get to the individual unit from a mass, I have to go through the grouping number. So I'm going to have beandles to get to beans. And a beandle is a mass in grams that I can get on my beandiotic table. And then getting from pounds to grams, that's just a conversion factor we've done before. So this is going to take a couple steps to go from pounds to grams to beandles to the group to the individual beans. So I'm going to start with 1 pound of a particular kind of thing. I know that there's 2.205 pounds in a kilogram. And a kilogram means 1,000 grams. And now I'm going to use the value that was given on the table for lentils. And it would have been, if I had had lentils, 10.2, they're very small. Grams of lentil beans, because they're small, in a beandle. And now I'm just going to use that grouping idea. A beandle means 100 beans. What kind of beans? We're talking about lentils. When did that matter? That only matters for the step where we use the beandiotic table. So we started with 2 sig figs. This conversion factor has 4 sig figs. Because we're going between mass and weight, we're going between systems. This conversion factor has unlimited sig figs because it is defined. It is a prefix conversion. This one depends on the beandiotic table that we use. And the one we used only went to the 10th place, so this has 3 sig figs. And then this idea of how many in the group for beans and beandles is unlimited, so that's exact. It was defined. But on the periodic table, that 6.022 times 10 to the 23 group that we call a mole, that's going to be to 4 sig figs. Okay, so I started with 2 times 4 times unleaded times 3 times unlimited. I'm ending with 2. So I could say 44,000, but that would be ambiguous. So I'm going to say 4.4 times 10 to the 3 beans. Okay, so now to the periodic table. And on the periodic table, we have symbols that reflect information about the elements. And so here we see that we have an element, it's copper. The symbol for copper is capital C, lowercase u. Its atomic number is 29. Why is it 29? Because that is its number of protons. The atomic number is the number of protons. And that's what makes copper copper, having 29 protons. This number down here we know is a weighted average. It's a weighted average between all the isotopes that are copper, given their isotopic abundance. So we could say that this is the mass of an average copper atom. Is there really any copper atom that has that mass? No. But it does reflect the group. And the group has 29 protons, some neutrons, and 29 electrons. And on average, there are 63.546 AMU per atom. This is one way to interpret the meaning of that on the periodic table. An AMU, atomic mass unit, is a mass unit that is equal to 1.66 times 10 to the negative 24 grams. Really small. Why do we use something that small? Because protons, neutrons, and electrons aren't very massive. And so we pick a unit to measure mass that is appropriate to their size. But if we were talking about a whole group of this, and the group we're going to call a mole, that's a group that we refer to as the number of Avogadro, 6.022 times 10 to the 23 atoms. We could say that the average group, a mole, has a mass of 63.546 grams in that large group. And we refer to that as a molar mass, and this particular one is for copper. So molar mass is the mass of 1 mole. And how did this mole come to be this particular size group? And the answer is that was the way to make this number available to be used twice. The size of the group was picked to match the mass of an atom. Okay, so let's look at helium for a second. You know, how many helium atoms are in a mole? Well, a mole is 6.022 times 10 to the 23 atoms, or whatever particle you're talking about. So we can interpret this meaning here to be 4.0026 AMU per atom, or 4.0026 grams in the group that we call a mole. And that is the molar mass for helium. So why is a mole of helium so much less massive? And the answer is because helium atoms are less massive. Helium atoms only have 2 protons and 1 or 2 neutrons. Copper atoms have 29 protons and a lot of neutrons. It's kind of like saying I have a dozen mice and a dozen elephant. A dozen is a dozen. It's a group. Do they have the same mass? No. A dozen elephants is a lot more massive. Why? Because each individual elephant is so much more massive. And that's why helium has a smaller mass. Because the individual atom has fewer atomic particles. And so the group, which we call a mole, is going to have fewer particles, be less massive. So, why do we use this huge number? And the answer is to make numbers manageable. A mole of copper is only 22 pre-82 copper pennies. What does that tell you about the size of an atom? It must be incredibly small. That 6.022 times 10 to the 23 copper atoms is only 22 pennies and only has a mass of about 63.546 grams. So we use this large grouping number because it makes a huge number of very small things manageable. And we weigh instead of counting in the beginning with beans because it was convenient. But here, because atoms are so small, counting is not possible. And weighing, or getting the mass, is the only way that we can figure out how many atoms we have. You have a packet of work to do, and the first page is all about carbon. So I'm going to do the first few problems, 1, 2, 3, and 5, just to demonstrate how to do these kind of problems. The first one, number 1, says you have 5.62 moles of carbon. How many carbon atoms is that? So we're going from a group to the individual pieces. We need the grouping number, and the grouping number is 6.022 times 10 to the 23 anythings, in this case, carbon atoms, is a mole of carbon atoms. I get my number. The calculator reports 3.384364 times 10 to the 24. And I put in the units, carbon atoms. And it doesn't matter what order I put them in. I can say atoms carbon or carbon atoms. I started with 3 sig figs. This grouping number is presented to 4 sig figs. It is known more precisely. But if you know it to 4 sig figs, you're fine. So 3 sig figs times 4 sig figs means I'm going to stop at 3. 3.38 times 10 to the 24, don't forget the exponent, carbon atoms are contained in 5.62 moles of carbon. The second question just goes the other direction. Now we're going to start with some carbon atoms. 8.45 times 10 to the 24. Oops. I'm specific about the unit, atoms, and also the kind of atoms, the element carbon. This time I'm going to divide by Avogadro's number. Carbon atoms, atoms are pieces in the group we call a mole. And I'm doing that so that the units cancel. I've made a mistake here. I wrote 10 to the 24 for carbon, for the number of atoms in a mole, but it should be 10 to the 23. Sorry about that. And my answer is 14.03188831 moles. I started with 3 sig figs, divided by 4 sig figs. My answer should have 3 sig figs. So I didn't need to use the periodic table so far because I was going from the group to the pieces and then from the pieces to the group. But now the questions are going to ask things about mass. Okay, now we're going to do number 3, and this time we do need the periodic table. We're starting with 79.9 grams of carbon, and we're headed to moles. So now I need to use this number, and I'm going to interpret it as 12.011 grams in a mole. But that's only true for carbon. I started with 3 sig figs. I divided by 5. My answer should have 3. And then number 4 goes the opposite direction. Okay, so if I'm going from a piece, atoms, molecules, formula units or ions, to the group, moles, I need to divide by Avogadro's number, 6.022 times 10 to the 23, and that works for every kind of thing. If I'm going from moles to pieces, I'm going to multiply by Avogadro's number. If I'm going from moles to mass, now I need to use the molar mass given on the periodic table, and I'm going to multiply. If I'm going from mass to moles, I'm going to use the molar mass for that particular element on the periodic table, and I divide. Okay, number 5 says we're starting with 35.50 grams of carbon. And our goal is to go from grams of carbon and get to atoms of carbon. Well, I have to go from grams to moles. And then I can go from moles to pieces. Anything having to do with the mass, I use numbers given off the periodic table. That's how many grams in a mole. To go from moles to pieces, I use Avogadro's number. I started with 4 sig figs. This particular number has 5 sig figs. This number is limited to 4 sig figs. My answer should only have 4. One, two, three, 4. That number rounds up. Alrighty. So if you end up with some strange numbers, if you end up with, 10 to the 47 or negative 46, that's a calculator issue. We can talk about that through Zoom. So how will you know if you have the right answers? At the bottom of each page are all the answers, and the sig figs are correct. So if you come up with different answers or different sig figs, we need to talk about that. Thank you for your time.